going to take the prerogative to ask Ross to say a few words about Michael.
So thank you all for coming to, this is the 9th award that has been presented, annual award in honor of Michael Page. And before I start, I'd just like to acknowledge that Michael's father, Roger, is here, sat in the front. And Roger has come all the way from Thunder Bay, Ontario. And it's not really cold there yet, so I guess without the pandemic, Roger has come to this event every year. So I just wanted to say a few words about Michael. For those of you that don't know me, I'm Ross McGovray. I used to work in the Centre for Blood Research and in biochemistry. So just clarify that. So Michael was actually born in Thunder Bay and went to the local collegiate, Port Arthur Collegiate, where his father, Roger, was the teacher for chemistry and physics in grade 11 and 12. Mike then went to Carleton, where he graduated with his BSc in biochemistry. And then he came to UBC to do a PhD with me when my lab and Peter Cullis's labs were in the pharmacology building. So here's Michael graduating in 2004. His thesis was actually on trying to convert a bacterial trypsin-like enzyme into a blood clotting-like enzyme. And he made about 13 different mutations, introducing loops into this protein to try and make it look more like human thrombin. So he was very successful as a grad student, published papers. His main work was done in collaboration with Natalie Strinadka on the three-dimensional structure of the mutant proteins that he was making. So during his time here, he was awarded a Canadian Blood Services Fellowship for both for two-year terms. He was also very good at mentoring others. This guy was literally an undergraduate student working under Mike by day, and he was the bouncer at Darby's on 4th Avenue by night. Anyway, Mark was so impressed by Mike that he stayed on to do a PhD, and now he's a faculty member in Melbourne. And unbelievably, a father of a child. Anyway, the thing about Mike was that as well as his academic excellence, he always had this great joyful life. And whether it be drinking at our Friday afternoon sessions in the lab in the good old days, or watching his beloved Vancouver Canucks on TV with his dog, Mike was just a great guy to be with. So after he graduated with me, he went to work with Enrico de Serra in Washington University in St. Louis. And I won't read this because Roger is going to just mention this, but those people that know Enrico de Serra, he is not easy to please, and Mike pleased him a lot with all of his academic research that he did there. Following that, Mike went to the University of California, San Francisco, working under Charlie Craik's mentorship as a junior faculty member in the Department of Pharmacology, I think it was. There, he started working on an idea he had for these restricted interaction peptides. So these are peptides that have got a hydrophilic part in red, hydrophobic part in blue, and then some sort of imager in yellow. And the idea is that you could inject these into people and they would make their way into cells, and then you could actually image where the protease has clipped the hydrophilic piece off, because the hydrophobic bit would insert into a membrane and you'd be able to spot it. So this is an example, this is an MRI using one of these peptides, and the bits in red, I think this is a pancreatic shot of an imaging agent where trypsin has actually been cleaving this particular peptide. So Mike formed a company. He had his patent was eventually issued, and then unfortunately Mike died very suddenly in Oakland on his way home from the lab, and tragically he was aged only 36. So to try and remember his name in biochemistry in the Center for Blood Research, we initiated this Michael John Page Award, which was initially supported by the Department of Biochemistry and Molecular Biology, the Center for Blood Research, as well as the Page family. And I'm very happy to say that Roger Page has now endowed the fund for this award, so it will be awarded in perpetuity. So that's a brief introduction of why we're here. As I said, this is the 9th annual award given out in Michael's name. So I'd like to ask Dana to introduce this year's winner.
So our winner this year is Dr. Miffy Cheng, and she's going to talk to us about how she's passed the shuttlecock around and how the bounces in her career helped her achieve scientific excellency. And I'd just like to say that there were a lot of applicants for this award, and you were the successful one. So please come down and give the talk.
I would like to thank a lot of people before I start my presentation, and thank you very much. I feel very honored to be here to talk about some of my research and my experience, but also feel extremely honored to be awarded this award. And I will start by talking a little bit about where the shuttlecock come from. So let's see. So it was also really nice to hear a little bit about Michael's experience and how he had a lot of passion for his research in science, as well as passion for life. And today I'm going to talk a little bit about how the two things in my life kind of tied together, and how I ultimately started my scientific journey, and the stuff that I learned from it, as well as the passion I have for science. So to start off with, I want to introduce the game of badminton, which I feel like most of us here probably have heard of it or played it before. It was first introduced in 1860s, and it was quickly became very popular in Asia and Europe. And as this popularity kind of grew, it became a sport that is played in a worldwide scale. It's a game that can be played in both a single or double game. And surprisingly, if you look at the size of the stadium, it doesn't really quite look like the football or soccer stadium that you see with a really big crowd. But bear in mind, there's actually a big fandom for this sport. There's a reason why, and I'm going to play a quick video and to show you why everyone is so excited about this sport. So I'm just going to quickly show here. I think. Oh, no sounds, but the commentator are all really excited while they were playing. It's a really fast-paced sport, and as you can see, there's a lot of movement. It's very exciting, and it's missing the sound effect here, but there's a lot of cheering actually in the gameplay. Yeah. So from hearing the laughter from the audience, we can tell that it is a very exciting game. And kind of coming back to badminton and myself, I think one of the things is that I wasn't actually a badminton player when I was a bit younger. I actually focused more in netball and hockey when I was in the UK. And it was not until grad school that I started to pick up the sport again and start playing badminton during grad school and all the way to now. As I kind of started my scientific journey and kept playing badminton, what I realized is that there actually are a lot of similarity between the two things. And these are the attributes that I'm going to talk a little bit about today and how that kind of relate to my own experience. First of all, both things need skills and techniques. And in badminton, in order to play a good game, a competitive game, you will need to know how to play certain shots. For example, if you're at a net, you want to play some net shot or drop shots. Or maybe in a more aggressive gameplay, you want to be able to kill the shot by playing a drive or a tap. Or sometimes in a difficult situation, you want to be able to clear or lift the shuttlecock so that it gives you more time to recover from your positions. And this is the same with science. In order to plan experiment and execute the research, it's pretty important for one to actually learn a bunch of skills and techniques. And for myself, as a nanomedicine scientist, what I've realized is that in a multidisciplinary field, you have to learn a lot of different things. And for me, I learned how to synthesize compounds, analyze them, formulate them into nanoparticles, do assay and evaluate them, as well as do in vitro and in vivo imaging and therapeutic studies. So my story began as an undergraduate in the UK, in a small city called Hull. And I started my undergrad in University of Hull as a chemistry student. And I spent my summer working in a lab and a compound that I pretty much fell in love with right away. And it's the porphyrin ring. And I loved the science there, and I decided to carry on and did my graduate degree, where I looked at two family of porphyrin compounds during that time. And you might ask, why do people care about porphyrin? Why people do research on porphyrin? One of the reasons why is it is the color of life. And when I show you the tetrapyrulic unit, it might not appear to you what they are immediately, but as we have a lot of blood expert here, we'll recognize this compound once we have the iron metal chelated inside. It's a key component in heme. You can also find porphyrin derivatives all over the nature. For example, chorin in vitamin B12, and also chorin that you can also see in chlorophyll, which is a really key component in terms of converting photo energy into chemical energy and enable photosynthesis and life. So when I started my PhD, I was investigating this technique called fluorescence guided surgery. It is a technique whereby the patient will be administered with a near-infrared compound. And ideally, those will accumulate in the tumor. And it's a very simple concept for the surgeon to then remove anything that is fluorescent. This is a very simple and interesting concept because it allows the surgeon to remove any cancerous tissue in real time. But there are some inherent problems, and during my PhD, one of the biggest problem is that light has limited penetration depth. So in order for the surgeon to really see where the tumors are, it means that we want light to penetrate deeper, and therefore we will need fluorescent near-infrared fluorescent dye instead. There are only very limited commercial near-infrared dye. They often are very hydrophobic and very hard to modify, and therefore aren't really used for fluorescence guided surgery very much. And so for me, I focus on a group of compounds called BODIPs. It stands for boron dipyromethane. They are a family of porphyrins, and they are extremely versatile to be modified to tune its wavelength so that it can exhibit near-infrared fluorescence. But also they can be modified to have different conjugation moieties that can then conjugate with biomolecules that could be used as potential targets. And BODIP stuck with me for a while, not only during my PhD, but also my cat is named after boron dipyromethane, short for Bo. It's not in his birth certificate because it's a bit too long. And back to the science, during my time, I also looked at the conjugation and the bioorthogonal chemistry with these dye against peptide, proteins, and antibodies. And in my PhD, I did a lot of synthesis in terms of designing and synthesizing different compounds, including all of these different BODIP dye with different wavelengths. And as you can see, they all bear a similarity, which is the azide moieties that is shown here. The reason why the A side is there is because I wanted to use click conjugation, which, if we're aware of the Nobel Prize this year, is what was awarded for chemistry this year. And during the time when I was doing my PhD, the click chemistry has become really, really popular. And there are more and more needs for bioorthogonal chemistry, especially for microscopy. And I looked at the conjugations using click chemistry with diazonium alkyl linker, and was able to produce a library of different wavelength dye that can be very easily conjugated to proteins that could potentially be very useful for microscopy. I also looked at the ability of these dyes to conjugate to antibodies. And as I mentioned, near-infrared dye tends to be quite hydrophobic, and they do aggregate quite a lot. So I looked into different strategies by using pegylations in the actual small molecule itself, which significantly increased the solubility and enabled me to conjugate to an IgG antibodies. We used some really interesting labeling reactions where we can site-specifically label the disulfur bridges without breaking the antibody apart. And we can also identify exactly the location and how many dyes is on the antibodies. And like I said, the ultimate goal at the time was to use these antibody dye conjugate for fluorescence-guided surgery. So they have to be pretty photostable because you don't want the surgeon to perform like a surgery in the mid-time and then the signal kind of disappears. So I was able to also see that these dyes are extremely photostable, and it has a wide range of usage, especially if you're trying to target certain receptors. And in this case, I used the Herceptin antibodies for targeting HER2 receptors. So it comes to all the techniques and all the skills that I learned. And as a chemist, I definitely learned how reaction works and how to set up reactions, but also some essential techniques such as working up reactions and purifications, where I did a lot of column with a lot of colorful compounds. And learn how to troubleshoot problems when they come, as well as find answers in the literature and books and ask some basic questions. Here was one of my favorite books when I was doing chemistry. It's a great book that many people use. And also trying to always carry on with different type of reaction, because you never know what works and what doesn't. The only way to find out is don't stop trying. And one very last thing is I also learned how to drink a lot of coffee and tea. And this is a great opportunity for me to chat with my colleagues over a cup of tea or coffee. Also sometimes beer, but it's better right now to in the afternoon to drink tea. Where I had a lot of inspiration during those kind of time having coffee and tea with my colleagues. So everything is great, thumbs up. And it perfectly takes me to the next part of the talk, which is communication. In badminton, especially if you play a double game, you would like to be able to communicate with your partners, because it is a game that requires more than one person. You want to be able to communicate with them so they know how to orientate themselves in the court, and not clashing and crashing into each other would also be a good idea. As scientists, it's very important for us to learn how to speak to fellow scientists, but also very important to present our research to the public so that they can also get a scope on what we're doing too. And during that time, I had 2 outreach events that was very fun and interesting. The first one is STEM for Britain. It's a competition-based event whereby student or postdoc can be selected to go to the parliament and present their research to the MPs. And I was very lucky too to have a lot of media coverage as well as an interview with BBC Radio to talk a little bit about my research. The other event that I attended is the Soapbox Science. It was an initiative that was created to advocate women in science. It's a very fun experience where they give you a box that you stand on. And I grabbed a bunch of friends who helped me out with all the props, but I basically stood on a box and started talking about my research in front of a shopping mall. It was definitely a little bit awkward at first, but it came around to a really fun experience where I was also trying to use Star Wars theme analogy to represent some of the concepts for fluorescent-guided surgery and the development of its approach. And when I finished up my PhD, the next thing I did was I decided to open a new chapter in my life and leave the UK and come to Canada. So I went to Toronto to do my first postdoc at Princess Margaret Cancer Research Centre, where I kind of have a bit of transition from my research to moving away from molecules and antibodies and started diving into the nano realm. And this is also where creativity and strategy kind of comes into my career. And as I mentioned, once you learn a lot of skills and techniques, it's time for you to use them in different ways. And it's similar in badminton. In order for you to play very creatively, you have to first know how to do certain things. And once you can achieve that, you can actually play some really interesting shot that no one expects, and it might throw off your opponent and allow you to win the match. And this is also the case with nanomedicine for cancer, where strategies are very important, especially if we look at the current drug. A lot of them are one treatment for all. We have to consider, though, that there are not only inter-patient variations, but also intra-patient variations where cancer cells can actually metastasize into different organs. And if we look even closer, we can also find that not every single cancer cell behave in the same way. There's actually a lot of intra-tumor variation as well. Therefore, maybe we should change our strategy and start looking for a customizable and personalizable nanomedicine rather than try this one fit-all approach. And similarly, in nanomedicine design, the more conventional way of doing so is have one carrier and load drugs or label them onto the surfaces. It's all good until you wanted to load a lot of things and label a lot of different agents that have different modalities. And this creates problems, including a very complicated synthesis and purification steps, making scaling up and reproducibility pretty difficult. So a different approach that I was looking at the time was the one-for-all approach, whereby the drug or the imaging agent is actually part of the lipid building block, and it can then self-assemble into nanoparticles, which is a much more elegant and simple way at looking at designing these particles. But the main thing is you have to be able to synthesize those building blocks. So I took the knowledge I had from my PhD and decided that I can also turn them into nanoparticle building blocks, whereby I designed a azabotipi lipid that has a phospholipid phospholipid group that is conjugated to it. And these lipid can self-assemble into a liposomal structure, giving a very similar properties to regular liposomes, but have very interesting optical properties that is not seen when it is in its monomer form. I also delve a little bit deeper in terms of trying to understand these systems, in terms of why we obtain these optical properties, and it's due to a specific alignment that occurs inside the liposomes and how these aggregate. I found that these particles can be also used for optical imaging, and there are two forms of these particles when they're injected in vivo. They have an intact form whereby the fluorescence is highly quenched, and they can be used for photoacoustic imaging. So as it circulates in vivo, you can track where they are. And when the particle reach the tumor, they will become disrupted. And when they do become disrupted, you can also use fluorescent imaging to track them as well. And this approach also extended to a different compound. And I also investigated a compound called texafrin. It's very similar to porphyrin, where you can chelate different metals in them, except for the fact that texafrin has a bigger ring. And the ring can actually chelate trivalent metals, such as indium-111 and lutetium in this case. And it's very interesting because texafrin, when they chelate the metal, they inherit certain properties. And for indium-11 being a gamma emitter, it can be used for radio profiling and imaging. Whereas the lutetium becomes a photoactive agent and can perform fluorescent imaging and photodynamic therapy. So I put together these two lipids from the same compound, just different metals, and assemble them into a nanoparticle, and also label them with a PSMA target, which is a prostate-specific membrane antigen target. As you can see on the right-hand bottom corner, we can selectively target those PSMA positive receptor tumors over the one that's negative, but also the fact that the indium allow us to track where the particles are going, giving us not only where the tumors, how much of it is being accumulated in the tumor, but also the PK and the biodistribution profile. And lastly, having the photoactive agents means that it can act as a photosensitizer. And when there is light and oxygen present, you can perform photodynamic therapy by generating these reactive oxygen species, which we're also able to show significant tumor inhibition, as well as no significant damages in terms of acute toxicity. This was, oops, just skip the page. This was research that was conducted with some of my colleagues, and one of them is an exceptional artist, and she was able to create a really fantastic cover art here, which I have to showcase to everyone. And this study is also featured in the Molecular Pharmaceutics special issue about Canadian nanomedicines. The next thing I want to talk about is perseverance. We all know that in badminton, as we saw in the previous video, it doesn't always go to the result never goes to what you want. Sometimes you can have a bad game, you're not playing the shot you want. But the thing is, if you don't give up, there's always a chance for you to turn the game over and still win the match. And there's no one better than Terry Fox in terms of he's the prime examples of perseverance, where he have been able to run across Canada through his Marathon of Hope and raise a lot of money for cancer research. And when I was in Toronto, we're obviously also inspired by this perseverance, and we would get together each year and go for the local Toronto annual Terry Fox run and raise some money for the Terry Fox Foundation. And during the pandemic, there's a lot of time where we all had to stay at home, and it was also a time for me to evaluate a little bit about what my goal is. And during the pandemic, I got to learn a lot more about the lipid nanoparticles that was pioneered over here at UBC. And so I decided to move on with my career and delve into something else in terms of research. So I decided to come and move to Vancouver. And very fortunately, I joined Dr. Peter Cullis's lab, where I had the opportunity not only to continue some of my research in liposomes, but also try out new research in the lipid nanoparticle area. One might ask, Paul Friend was very interesting. Why are you interested in lipid now? I think the reason is both things are very essential to life. And I think I'm very attracted to both the compounds. And when we talk about lipid and why it's so important, it is partly seen as the origin of life. We have millions of cells, billions of cells in our body, different type and different properties. But one thing in common is that a lot of them have these plasma membrane. And if we break it down further, the membrane is actually consists of a lot of different molecules, proteins. For example, we have glycoproteins as well as cholesterol and phospholipid in the membrane. But if you dissect even further, you realize majority of it is consists of this lipid bilayer. And the lipid bilayer are only formed by these membrane lipids. These membrane lipids have some very important properties, including the hydrophilic head groups and the hydrophobic tails. And by altering the volume and the area of these two components, you can create different geometry and therefore yield different nanostructure from these simple lipids. And this led us to a lipid nanoparticle, which utilize a lot of that kind of lipid properties to enable the encapsulation of nucleic acids, resulting in what we now know as the LNP lipid nanoparticle. It mainly consists of 4 different components, and the more important one is ionizable lipid, which was developed here at UBC, whereby at a lower pH, it becomes positively charged, enable it to interact with the negatively charged biomolecule. And when you raise the pH back up to physiological pH, it will become neutral, and therefore it makes it a lot more biocompatible and less toxic comparing to cationic lipids. And there are also very important components, such as the helper lipid that give some of the structure, the PEG lipid, as well as the cholesterol that are essential part to formulating a nanoparticle. And there's a lot of success in the lipid nanoparticle field, including the first RNAi drug that was known as Onpattro, as well as what we now all are really familiar with, which is the COVID mRNA vaccine that was first developed in 2020. And in the Catalyst Lab, we continue to look at how these platform functions, the way that they are assembled and the way that they are formulated, and the formation of them, especially the different type of morphology. And in our lab, we continue to look at how those structure activity relationships towards these LNP can help to improve some of the efficacy of the gene delivery. There's endless potentials with this LNP mRNA, which is something that got all of us very excited, especially when different cargo can be loaded. For example, gene editor such as CRISPR-Cas9 can be loaded in these LNP and delivered to a disease site, whereby these gene editor can knock out disease-causing genes. And also, it have the ability to produce monoclonal antibodies, but also treat diseases that are caused by the deficiency of the lack of certain proteins by replacing those proteins. And again, vaccine is something that we're really familiar with now. But it's not only limited to the COVID virus, but also other type of viruses as well. And lastly, with cancer research and immunotherapy really catching a lot of attention, the LNP mRNA can also be potentially used to generate CAR T cells in an extent that it could also be generated in vivo. So these are all really exciting avenues, but there are still some delivery barriers that exist with these great platforms. And this is the reason why we're still doing a lot of research in this area. And this include, for example, delivery barriers such as an in vivo kind of setup, whereby when we inject these nanoparticles, they can be recognized by immune system and could be very rapidly cleared out. As well as mRNA, as we all know, are very sensitive to nuclease and can undergo degradation in vivo. So when it comes to some of the other issues, there are something that I'm particularly interested very interested in, and that is the endosomal escape of these nanoparticles. There have been some research that suggests only around 1 to 2% of sRNA actually get released in the cytosol. So the question really lies in terms of, can we find ways to improve this limitations by allowing more of the RNA to actually be released in the cells? There are a lot of different approaches and different ways to do that. And in one of the studies that we're currently working on in collaboration with the Toronto lab is by, again, introducing a porphyrin lipid into the LNPs. The basic principle of how this could potentially work is that you have these porphyrin lipids that can easily be incorporated into the LNPs, and having reactive oxygen species that can be generated by light. These nanoparticles can then be uptaken, and these porphyrin lipids can migrate to the endosomal membrane. And when you shine light on it, the reactive oxygen species, which in a very controlled manner, could actually break apart the endosomal membrane and release more of these RNAs. And this is actually feasible, and we've been able to show that. And what we see is that by replacing the helper lipid, which is the DSPC in the Onpattro formulations, we can use these porphyrin lipid and still form a very stable structure that highly resemble the Onpattro formulations. And these particles also retain some of its reactive oxygen species generation properties at different pHs as well. We have been able to see through microscopy how this functions. And as you can see on the microscopy imaging figure here, before you actually apply the laser, you can see a lot of these siRNA reside in the endosome, where the porphyrin is within the membrane. And by hitting it with a laser for only 30 seconds, we can already see an incredible improvement in terms of the release of these siRNA. As you see, the signal of the green have now migrated into the cytosol. So this is incredibly exciting. And we also wanted to look at whether this is feasible in vivo. So we decided to use TEM as a technique to observe any subcellular localizations in vivo. And we replaced the RNA with gold nanoparticles, as this is a way for us to actually visualize using the technique. And what we did was we injected the porphyrin LNP with gold nanoparticle into tumor-bearing mice. And at a 6 hours drug-like interval, we will hit the tumor with a laser, and we will extract the tumor and look at where these gold nanoparticles are. We saw some very promising results, especially when we don't have any light. We can see that the gold nanoparticle reside in these endosomal structures, and at both cases, when you can see when there is these kind of patches around the endosome. And when we irradiate it with light at only 50 joule per centimeter square, we can see that right after the laser treatment, there are some migration of these gold nanoparticle, especially as well as some of the membrane being disrupted around the area. And at 18 hours post laser treatment, we can see very clearly that there is no more of these kind of structures surrounding the gold, and that the gold nanoparticle are in a different space as observed here. So last but not the least, I think in both cases, badminton and science are really fun things, and they also for everyone to enjoy an experience. And I kind of took the opportunity after my experience in my scientific journey and joined multiple different societies and scientific community. And one of the things that I also did is take up as a mentor in some mentorship program, including when I was in Ontario, the Ontario Rising Star Network that tried to bring together different trainees across Ontario, and also connect cancer scientists from different fields. And not only that, I also, when I joined UBC, I also started in the biochemistry and molecular biology mentorship program, where I was able to mentor some students, and I was able to share some of my experience, my resources, and some of my connections. And during the pandemic, it was very difficult to have any outreach event because we were all kind of stuck at home. But I had the privilege to join this youth symposium that was actually hosted online through a software called GatherTown, which you have your own avatar and you can walk around. And during that time, I had the opportunity to meet a high school student and tell them about the research and the development of the COVID vaccine, which was all very exciting. And this leads me to coming to the end of my talk. I think I've been really fortunate, and science has taken me onto this journey where I was able to travel from place to place. And I can now proudly say that in this scientific journey, I was able to meet a lot of people and people all around the globe. During this time, I met a lot of great people, including great mentors and great colleagues who I have become friends with and are going to always be friends with and it's been an incredible journey and very long list of people that I would like to thank. And one thing to mention is without them, it's not possible for me to generate any of the research we just saw, but also they gave me an incredible experience and an incredible journey. And this is definitely not the end. Hopefully this is only the very beginning. And lastly, I would like to thank my family, my husband, Owen, and my dad for their constant support. As we all know that research is not an easy route, but it's been really fun for me. Thank you, everyone. Yeah, I'm happy to take any questions if there's any.
This is more on the badminton side, but it's like, can you describe what level of involvement you have with the badminton? Are you part of any leagues or anything like that?
I did play a little when I was in mostly recreational, but I played in a league when I was in Hull. I'm definitely not as good as the people you saw in the video. They are the world-class level. But I've also played a bit here at UBC, where I met a lot of great friends, and a lot of people from the lab actually also play badminton. So mostly recreational, but I do play a little bit in leagues and things like that with my husband being my partner. That's why communication is important.
So what are your career goals?
There are actually many inspiration in my life, and I think Peter being obviously a great mentor and some great examples to be able to juggle between industry and academia, I think that will be very exciting. But I do enjoy doing research and mentoring students, as some of my students are actually here today. So academia is something that I'm still ultimately very interested in. And I hope to, I mean, I'm no one to say that I can inspire anyone, but that is my goal ultimately.
Any other questions? Thank you very much, Miffy.
Thank you.
Now we'll hear from Mike's dad.
It's on. Well, it's very nice to be back here in the UBC facility that Michael worked on his PhD. And I wasn't going to really say too much other than make a congratulation comment to the young lady who just received the award. But I thought a little bit more about it, and I said, well, this might be my last trip. Maybe I'll add a few more words. And I thought you might like to hear a little bit more about Michael. Once he got his PhD here, then I'm going to read a eulogy that was written by his mentor professor in Washington University in St. Louis. And this is how it reads. Michael joined my lab at Washington University in 2004. After obtaining his PhD with Ross McGilvery, he contacted me by email over the summer of 2004 with a clear plan for his future in my lab. Most of the things he wanted to do were exactly the same as those that I wanted to do. So I offered him to join the lab without hesitation. What followed from 2005 to the end of 2009 was some of the best work ever done by my lab. Michael and I co-authored 10 papers, and he was first author in 8 of them. These papers covered enzymology, protein engineering, and X-ray crystallography. The reviews were published together on serine proteinases and ion binding to proteins, have become key references in the field. As a testament to the quality and impact of his work, Michael received a 2-year fellowship from the American Heart Association, extended for a 3rd year, and then followed by a prestigious K Award. In the top 1 to 3%, Michael was a brilliant young man, a real pleasure to have in the lab, and without a doubt, one of the finest young scientists I have ever seen. I treated him as a colleague because his knowledge and maturity were uncommon for a person of his age. I will miss his ingenuity, his deep knowledge, and enthusiasm for science, and I will miss his great sense of humor that made my lab such a great place to work. So that gives you a little bit of background of his character. And so now a couple more things I'm going to add, not so much with Michael, but the presentation today was very interesting because the 3rd person that got this award, and I believe it was the 3rd person, she focused on what she likes to do, flamenco dancing. Flamenco dancing, and she said that to perform as a flamenco dancer is not simple. It takes an awful lot of thought, control, and knowledge about all the separate moves and how they're done just right. And she said that very easily applied to the science that I was doing, that you had to follow the same kind of feeling when you were doing it. And over the years, we've had quite a variety of different people that have won the award. One was captain of the Edmonton football team. Yeah, a big fellow. I was intrigued with that gentleman. Another one that came from a very prestigious university in Germany. And so the university here does draw on people from across the country. As a closing, I'd like to comment on Terry Fox, because he passed away and stopped his walk right outside Thunder Bay, Ontario, where I live. And there is now a beautiful statue right on the highway of Terry Fox. And of course, every year you've got so many people that do the walk to raise more money for cancer. So I think those are the key things. And I don't know if I'll be coming back out again. I'm getting a little bit more on the twilight zone. So you sort of think, well, you know, and I will make one last comment. Michael carried on his work after he was finished at Washington University at the University of California in San Francisco. And there he had tremendous success with what he was doing. And sadly, his life was short there, but he did achieve things like Nature Communications. His last paper was published in it, and a patent that has now been released by the American Patent Bureau. And those were attributes. And they have named a research symposium after him. And this is for PhD students. I just came from there yesterday because we had the presentation of 4 of them had to get up in front like you did and did your presentation. Well, they had to do that. And these were PhD students. And that, on top of it, the gentleman who got that going was one of the big billionaires in the States. And now the program, the discovery level program, is supported by $110 million. And the earnings from that go into supporting the PhD students that are in there second last year and last year. So his name and his legacy is certainly there. Thank you.
Thanks very much, Roger. That was very entertaining. And I think we're basically a wrap. So, Miffy, congratulations again.